Hi, welcome to the next video. So I'm going to start this video off with example 7.7. Okay, so let's do parts A and B. Suppose X and Y are continuous random variables. With joint probability function. Joint probability density function, f of x is equal to 1/2 x e to the negative y for 0 less than x less than 2, y positive, and 0 elsewhere. Okay, so that is our joint probability function for continuous xy. Part A is find the joint cumulative distribution function. Of x and y. Okay. So to do this, we're going to do this in several steps, and so I'll call them cases. Okay. So depending on where in the domain you're looking, this function will be defined differently. So let's look at case 1. So for case 1, we're going to consider x greater than or equal to 0 and any real number y. Okay, so we're going to restrict the values of x and y that we're considering to x greater than or equal to 0 and any real number y. Okay, so let's find the joint cumulative distribution function of x and y for these x and y. So capital F of x comma y is now going, by the definition, is equal to the integral from negative infinity to y, negative infinity to x, of little f of s comma t ds dt. Okay, so s is a dummy variable for x and t is a dummy variable for y. Okay, so we're using calculus to calculate this integral, and so for these x and y, okay, so for this domain of integration, little f is equal to 0, because for these x greater than or equal to 0 and y any real number, that does not fall into this range of x and y, where f is this. Instead, it's the elsewhere part, which is 0. So little f of x comma y. Little f of x comma y is 0 here. And so this little f of s comma t is 0. And so it's 0 ds dt. And so if you integrate over 0, you get 0. And so capital F of x comma y is 0 for those x and y. Okay, and so that is case 1. Okay, that's the first piece of capital F of x comma y, that we found. Okay, so let's continue. Let's go to case 2. Okay, so for case 2, we have for any real number x, and we have y less than or equal to 0. Okay? And so for those x and y, capital F of x comma y is equal to the integral from negative infinity to y, integral from negative infinity to x, of f of s comma t ds dt. Okay, so now this is for any real number x and y less than or equal to 0. Okay, and so for these values of x and y, little f is also 0. And that's because y is less than or equal to 0, so y is not positive, right? And so little f is 0 here, and so now this is equal to the integral of the same integral, same place, 0 ds dt. And that integral is 0. And so capital F is 0 here. Okay? So that's case 2. Capital F is 0. Okay, so that's the second piece of the joint cumulative distribution function of x, y, capital F. Now let's go to case 3. And so then afterwards, when I do all parts, I'll put down the final function. Case 3 is for 0 less than x less than 2, y positive. Okay, so now we're going to consider x between 0 and 2 and y positive. Then capital F of x comma y is going to equal to the integral from negative infinity to y, integral from negative infinity to x, of f of s comma t ds dt. That's what it is, right? Okay, so now it's this function here, because x is between 0 and 2 and y is positive. And so now we're just going to replace that function here. So it's the integral from negative infinity to y, so integral from negative infinity to x of 1/2. S is the dummy variable for x, and t is the dummy variable for y. And so you get that integral. Okay? Okay, so you have to know how to integrate, you have to know how to use a dummy variable, and you have to know how to evaluate a definite integral. So this is equal to, now we're going to separate the two variables here. And so we're going to get the integral from 0 to y of e to the negative t dt times the integral from 0 to x of 1/2 s ds. Okay? How do I do that? Well, so if it's from 0 to 2, x, right? We're going to integrate from 0 to x. We're going to start at 0 and whatever value of x we chose, and that's going to be 1/2 s ds. For y is only, f is only this when y is positive at 0 everywhere else. So we're going to start at 0 and we're going to end at y, and it's e to the negative t. T is the dummy variable for y. So it's e to the negative t dt. So we're going to integrate both. You integrate both these and multiply the results, and you get that's equal to 1 minus e to the negative y times, okay, it's 1/4 x squared times 1 minus e to the negative y. Okay, so for that you just calculate this definite integral, calculate that definite integral. You get the expression of y and expression of x. You multiply them. You have 1/4 times x squared times 1 minus e to the negative y. So that's capital F for those x and y. That's case 3. Okay, so that's the third piece of capital F. Okay, and so now for the fourth case. So for case 4, you have for capital X greater or equal to 2, y positive, then capital F of x comma y is equal to the integral from negative infinity to y, integral from negative infinity to x, of f of s comma t ds dt. Okay, so that's capital F. And this is equal to the integral from 0 to y, integral from 0 to 2 of 1/2 s e to the negative t ds dt. Okay, so what does this mean? Well, if x is greater or equal to 2, then f is only non-zero for x values between 0 and 2. So if x is greater or equal to 2, you're going to integrate all the way from 0 to 2. And then whatever you go past it, right? So if you're integrating, here's x greater or equal to 2, here's 2, here's 0, right? F is 0 here. Little f of x and y is 0 here, and little f is 0 here, right? So little f is 0 here, and here. And so if x is greater than or equal to 2, you're going to just capture that part and you're going to integrate from 0 to 2 when x is greater than or equal to 2. Okay, and so for x greater than or equal to 2, you integrate from 0 to 2. For y positive, then since y is positive, here's 0, right? F is 0 when y is negative. When y is positive, here's y, and so you're going to want to integrate that part from 0 to y to get the y part, and 0 to 2 for the x part. Okay, and then that's f there. And so we're taking only the part of this domain where it falls in that range. Okay, so not all of it. And so then you calculate that f integral. And so to do that, you can separate the two. You don't have to, but it's an easier way to explain it. Is integral from 0 to y of e negative t dt times the integral from 0 to 2 of 1/2 s ds. Okay, and so now you can integrate both of those and then multiply them. You get 1 minus e to negative y. Okay, and so that's capital F for that fourth part. And so you put those together and you get capital F over the entire domain, its entire domain. Okay? Okay, and so this is case 4, this is capital F for that case. Okay, so that's case 4. So in conclusion, I'm going to write down what capital F is over each part of its domain. So I'm going to express capital F as a piecewise function. Okay, so the conclusion, the answers to the problem, find the joint cumulative distribution function of x and y, is capital F of x comma y is equal to 0 for x less than or equal to 0 and y any real number. 0 for negative infinity less than x less than infinity, y less than or equal to 0. It's 1/4 x squared 1 minus e to negative y for 0 less than x less than 2, y positive, and 1 minus e to negative y for x greater than or equal to 2, y positive. Okay, so capital F is this function. Okay, and so these are each of the cases, and now that's it. So that's the answer to A, part A of this problem. Okay, so A is solved. Okay, so let's go to B. So part B of the same question. This is capital F here. Okay. So for part B, it's find capital P of x less than or equal to 1, y less than or equal to 2, and P of 1 less than or equal to x less than or equal to 2, 3 less than or equal to y less than or equal to 4. Okay. Okay, so this is little f and here's capital F. So we now have both little f and capital F. I'm gonna erase the top part here. I'm gonna answer as much as I can the top part. So maybe I try to keep little f and capital F on the board as long as I can here. Okay, so we have little f and capital F. So for part B, if we want to find the probability that x is less than or equal to 1 and y is less than or equal to 2, that's equal to capital F of 1 comma 2 by the definition of cumulative joint distribution function. The joint cumulative distribution function of x and y, right? That's by the definition. So this is capital F of 1 comma 2. Capital F of 1 comma 2 is the probability that capital X is at most 1 and capital Y is at most 2. Okay? And so, to calculate this probability, right, to find that probability, we're just going to find what capital F of 1 comma 2 is, but we found capital F here. So when x is 1 and y is 2, that's here. And so it's here because x is between 0 and 2, and y is positive. And so here it says that capital F of x comma y is that. So it's 1/4 times the x value squared. So it's 1 squared times 1 minus e to the negative the y value, which is 2. And so what you get is that this is equal to 1/4 times 1 minus e to the negative 2. Okay, and you can leave the answer like that. And so that is finding that probability, the probability that x is less or equal to 1 and y is less or equal to 2. Okay. So for the next probability, the probability that 1 is less than or equal to x, less than or equal to 2, and 3 is less than or equal to y, less than or equal to 4. And so for that probability, we're going to integrate. And we're going to integrate x between 1 and 2 and y between 3 and 4. It's going to be f of x comma y dx dy. These are the x values 1 to 2, and the y values are from 3 to 4. And so we're going to compute that definite integral. And so if x is from 1 to 2 and y is from 3 to 4, then we're looking at those range of x and y values, right? X is between 1 and 2, and y is between 3 and 4. And so it falls into the range of x between 0 and 2 and y positive. And so, wait, sorry. Sorry, that's capital F. Okay, so here, let's see, that's little f. Right, there's little f. So little f is that, for that range. So x is 1 to 2, y is positive when it's between 3 and 4. So we're going to substitute that little f for that. And so you get the integral from 3 to 4, integral from 1 to 2 of 1/2 x e to negative y dx dy. They just substituted f of x comma y for that. Okay. Okay, so now I don't need little f anymore, and I don't need capital F either. We use capital F for the first probability, and that's what we need little f for. Second one. So I'm going to erase all of this now. So I'll use the capital F and little f as much as I need for part B. Now the problem is reduced to just calculating that definite integral. So I know that I don't need those anymore because that probability is equal to this definite integral. Calculate this definite integral and we get that probability. So now I know that I don't need either of those anymore. Okay, so now, so you calculate that definite integral, and I'll tell you what that is. That's 3/4 times e to the negative 3 minus e to the negative 4. Okay, and so that probability is equal to that. Okay, so now we've answered the question of what both of those probabilities are. Okay. Okay, so if you want to see why that double integral is equal to that as practice, then, well, I'll show you. So side work here, I'll show you how you remind you of how you do a double integral, okay? Just for practice, we'll do this one. Okay, so the answer was that probability was equal to this. Substitute the appropriate f here, and calculate, you get that. So the side work is computing, let's compute this double integral, okay? Let's compute it and practice this. And make sure that, so you need to make sure that you know how to calculate a double integral correctly. Okay. So, so here's the integral from 3 to 4, integral from 1 to 2 of 1/2 x e to negative y dx dy. So I'm going to separate them into two integrals because the x and y are separate here. So I'm going to get the integral, the y integral is from 3 to 4, and it's going to be e to the negative y dy. That's the first integral. I'm going to multiply it by the second integral, which is the integral from 1 to 2 of 1/2 x dx. Okay? So 1/2 x dx, integral from 1 to 2 of 1/2 x dx, and then the integral from 3 to 4 of e negative y dy. So let's just compute both of those. So an antiderivative of e to negative y is negative e to negative y. If you take the derivative of negative e to negative y, you get negative e to the negative y. You get e to negative y. So that's an antiderivative of this. This is an antiderivative of that. So you evaluate from 3 to 4. We're using the fundamental theorem of calculus. Right? The fundamental theory of calculus says if you want to compute a definite integral from a to b, little f of x dx, it's equal to capital F of x evaluated from a to b, where capital F is an antiderivative of little f. So this is an antiderivative of the integrand, and you evaluate from the lower limit to the upper limit of the integral. Okay, and so this is times, so that's the first bracket, times, now an antiderivative of 1/2 x squared is 1/4, an antiderivative of 1/2 x is 1/4 x squared. Right? If you take the derivative of 1/4 x squared, you'll get 1/2 x. And so we're taking 1/4 x squared, which is an antiderivative of that integrand function, and we're evaluating it from the lower integral limit to the upper integral limit. So we're evaluating from 1 to 2. Okay, so that's by the fundamental theorem of calculus. And so then that equals, now you compute that, and so you get negative e to the negative 4 minus negative e to the negative 3 times 1/4 x squared from 1 to 2. So it's 1/4 2 squared minus 1/4 1 squared. Okay? And so then that is equal to, well, this minus this, the minuses cancel, you get plus. So this is e to the negative 3 minus e to the negative 4. Times, this is a 4 here, so 1/4 times 4 is 1, minus 1/4. Okay? And so now I'm going to just that part here. And so then that's equal to, well, 1 minus 1/4 is 3/4. Right? So 1 minus 1/4 here is 3/4, and then this is e to the negative 3 minus e to the negative 4. And so I just showed you is that, in fact, this is true. This double integral here is equal to 3/4 times e to the negative 3 minus e to the negative 4. Okay? And so that's side work, I'll call it star. That's the side work showing that that double integral is equal to that. Okay, and so that is example 7.7. Okay, so let's continue. Let's do another example, example 7.8. Okay, so example 7.8. So for example 7.8, let x and y be continuous random variables. With joint probability density function little f of x comma y is equal to 2xy plus 3/2 y squared for 0 less than x less than 1, 0 less than y less than 1, and 0 elsewhere. Okay? So let capital C be the region of points x comma y in the plane such that x plus y is less than 1. Find the probability that x comma y is in the region C. Okay, so let's read through the problem again. Example 7.8. Let x and y be continuous random variables with joint probability density function little f of x comma y, which is equal to 2xy plus 3 halves y squared for 0 less than x less than 1, 0 less than y less than 1, and 0 elsewhere. Let capital C be the region of points x comma y in the plane such that x plus y is less than 1. Find the probability that x comma y is in C. Okay, so let's find the answer. So, okay, solution. So let me start by drawing a picture of what C is. Okay, let capital C be the region of points x comma y in the plane such that x plus y is less than 1. So I'm going to squiggly underline that part. This is the part I'm looking at right now. Capital C is the region of points x comma y in the plane such that x plus y is less than 1. And so what does that region look like? So let's draw it. Okay, so here's the x-axis, here's the y-axis. All right, this is Cartesian plane. Okay, so x plus y, so let's look at x plus y equals 1. Okay, let's look at x plus y equals 1. And so let's, so for reasons that will make sense later, let's solve for x. X is equal to 1 minus y, okay? And so you'll see this choice once you've done this enough. So x equals 1 minus y is the same as x equals negative y plus 1. Okay, x equals negative y is this diagonal line that looks like this. Okay, so this line here that goes to the origin is x equals negative y. But x equals negative y plus 1 then is taking that line and moving it to the right 1 because it's plus 1 x, you're adding 1 to x. And so you're going to take x equals negative y, you're going to shift it to the right 1 because it's x. If it was y and if it was y equals negative x plus 1, you'd be shifting it up. If it's x equals negative y plus 1, you're shifting it to the right. So this is going to be by transformations, graphing transformations, this is pre-calculus. This is the graph of x equals y, negative y plus 1. Okay, so that's x equals negative y plus 1. For instance, when y is 1, x is 0. When x is 1, y is 0. Okay, and it's a line that goes through those 2 points. So that's x equals negative y plus 1, or x plus y equals 1. Okay. Now, the points that satisfy the inequality x plus y is less than 1 is either all below this line or above this line. And so you have to just decide, is it going to be above or below? Okay. So x plus y less than 1. For instance, let's take the point 3 comma 0, right? This point here. This point here, 3 comma 0. When x is 3, y is 0. When x is 3 and y is 0, that's x plus y is 3, and that's not less than 1. So this is the part that does not satisfy this inequality. This is the part that does. So that shaded region is all the points, not going past that line here, it doesn't. Okay, everything below this line, those are all the points that satisfy the inequality x plus y less than 1. And so since these are the points where x equals negative y plus 1, or that x plus y is equal to 1, now I'm going to change this solid line to a dotted line. Because now I want to depict the points that satisfy the inequality. Okay, so now I'm choosing a dotted line. So what that means is that the points on the line do not satisfy this inequality. That would make them equal. But what's below the line is the ones that do satisfy the inequality. And here's the x plus y equals 1 also. Okay, so the shaded region, these are the points such that x plus y is less than 1. This is region C. Okay, so that is a picture of region C. It includes the origin, right? And so if you plugged in 0 plus 0, that's less than 1. If you plugged in the point 0 comma negative 5, where x is 0, y is negative 5, 0 plus negative 5 is negative 5, which is less than 1. So all these points satisfy, or all the points that satisfy x plus y is less than 1. Okay, each point does satisfy the inequality, and those are all the points. So we found the entire set of points x comma y that satisfy the inequality. We found the region C. Okay, so we want to find the probability that x comma y is in that region C. So if we chose a point arbitrarily x comma y, what is the probability that point would be in that region C? Okay, so I'm just going to label a point x comma y here. It could have also been here though, right? So that, I'm going to erase that point, we don't need that anymore. That point could also be here though, right? So there's a chance that it won't be in, at least we think it won't be there. Now this little f, our joint probability density function, tells us that this is the probability when 0 is less than x less than 1 and 0 is less than y less than 1. Okay, and so what does that mean? So that means that that's our region C, right? This is our region C here. But then, if we look at this problem a little bit deeper, we see, first we have this line here. That's the line up there. Okay, that's a line. Okay, that looks more like a line. Okay, good. So that's our line there. And then it says that little f is this for 0 less than x less than 1, 0 less than y less than 1. So let's focus on this part. This is dotted and this is dotted. I'm not including the axes there because it's strictly less than's here. So this shaded region B that is above the x-axis to the right of the y-axis and below that line x plus y equals 1, this shaded part, not including any of the boundary points, that shaded part is the part of capital C where the probability is not possibly non-zero, which is equal to this expression, right? Everywhere else it's 0. So here, even though this is still a point in C, the probability is 0 here, 0 here, 0 here. Everywhere outside of here, by the definition of little f, our joint probability density function, the chance of us hitting with x comma y any of these points is 0. The only chance that that point is in our region C is that if it's in that region. Okay, and so with those two pictures, let's now start to solve the problem. So the probability that x comma y is in that region C is equal to the double integral over the region C of f of x comma y dx dy. Okay, so we're going to integrate over the entire region C and that probability function f. So now it's 0 everywhere else here. So it's only non-zero here. And so it's only for 0 less than x less than 1, 0 less than y less than 1. Okay, and so we're going to integrate this region here, right? If we're going to integrate that spot, then using multivariable calculus, what we would need to do is, this is the line x equals 1 minus y, this line here, right? This is y equals 0, this is x equals 0, right? Because the x-axis and y-axis extend. But let's just focus on x equals 1 minus y. One way to integrate this is if we say, okay, I'm going to look at the x part here. I'm going to integrate with respect to x first, right? Because that's what we have here. So we're integrating with respect to x first. And so that means integrating from 0. So here the x value is 0, right? On the leftmost part of that rectangle. On the rightmost part, it's x equals 1 minus y. So we're going to integrate from x equals 0 to x equals 1 minus y. And then this rectangle sweeps from y equals 0 to y equals 1. And so then we're going to integrate with respect to y from 0 to 1. And f is 2xy plus 3/2 y squared. And that's dx dy. That's y equals 1 there. Okay, so this is a separate picture. I'm going to separate that. So this is integrated now f of x comma y, which is this. it's that. That's f of x comma y for those values, but then to integrate it, we go from 0 to 1 minus y, and then y from 0 to 1. X from 0 to 1 minus y, and then y from 0 to 1. And that integrates over this entire triangle region. And so now it's just a matter of computing that definite integral. And so if you first do with respect to x here, you compute the first definite integral, right? From with respect to x from 0 to 1 minus y, what you get is you get the differential from 0 to 1 of 1 minus y squared y plus 3/2 times 1 minus y squared dy. Okay, so you get that definite integral. When you compute this definite integral on the inside, you get this, and now you integrate that from 0 to 1, and what you get is 5/24. Okay, so the probability that x comma y is in that region C here with this probability, joint probability density function is 5/24. Okay, 5/24. And so that's that probability. So that's the solution to example 7.8. Okay, so let's keep going. Okay, so the next section is 7.2.4, and it's on marginal distributions. Okay, so 7.2.4 is on marginal distributions. So definition 7.4. Part A. Let x and y be discrete random variables. With joint probability function, density function, f of x, little f of x comma y. The marginal probability functions of x and y, respectively, are given by f sub x of x, which is equal to the sum over y of f of x comma y. Okay, so they have to be discrete, right? This is for a discrete one. And so note that f sub x of x is equal to the probability that x, capital X equals little x, which equals little f of x. Okay, now f sub y of y is equal to the sum of all possible values of x of f of x comma y. And note that f sub y of y is equal to the probability that capital Y equals little y, which equals little f of little y. Okay, so this is the definition of the marginal probability functions of x and y, respectively. This is the marginal probability function of x, and this is the marginal probability function of y. Okay, this is the probability that capital X equals little x. But you're getting this from your joint probability density function. Right? This is the probability that capital X equals little x and capital Y equals little y. But you're using that to find the probability that capital X equals little x. And to do that, you just take this one and sum over all possible values of y. But such that the little x is this one here. Okay? And it's the same thing here. The probability that capital Y is equal to little y is summing over all possible values of x of little f of x comma y. Okay? So that is part A of definition 7.4. Okay, so I'll leave this up so you can write things down. Then I'm going to erase this and I'm going to put part B up of the definition. Okay? Okay, so this is important, so you need to write this down. This is for discrete random variables, okay? For discrete random variables, you have to use the summation, okay? For continuous, we're going to have to use integrals. But right now, we're using summations because we're dealing with discrete random variables. Okay, so you have to know this equation and you have to know that equation. Right? The words are all explaining what this is meaning, right? Okay? Those two are equations. That's the conclusion of, that's what this definition is giving you. Okay, so part B of definition 7.4. Okay, so part B, let x and y be continuous random variables with joint probability density function f of x comma y, little f of x comma y. Now look, so now it's continuous, right? In A it was discrete, now it's continuous. So the marginal probability density functions of x and y respectively are f sub capital X of little x is equal to the integral from negative infinity to infinity of f of x comma y dy. And f sub capital Y of little y is equal to the integral from negative infinity to infinity of f of x comma y dx. Okay, so these are the marginal probability density functions of x and y. This is the marginal probability density function of x, and this is the marginal probability density function of y. Okay, and so definition 7.4 part B gives you this equation, and it gives you that equation. Okay? Okay, so now we have the definition of the marginal probability density functions of x and y when you have discrete random variables and when you have in part A for discrete and part B for continuous. Okay, this is the probability capital X equals little x, and this is the probability capital Y equals little y. But for here, for continuous random variables. Okay, but you're getting that probability with a joint probability density function, right? Before we talked about just a probability density function where you had one variable, right? And so how do we get that from having a probability function involving two variables? These equations tell you how, okay? So from a probability density function involving two variables, you can get the probability density function of one variable from these two equations. In a sense, this is going to be more information, and then you want to get less information, saying what's the probability just when capital X is equal to some fixed number, right? This is telling you what the probability is when capital X is equal to some fixed number and when capital Y is equal to some fixed number. You take this equation, you calculate this integral, and you get what is the probability of capital X. Just capital X is equal to a fixed number. Okay. For this, you have to integrate over Y for X, and to find Y, you have to integrate with respect to X. In a sense, this is like summing up. The values of little f. Before you have to use a summation, but for continuous, but you sum up by taking an integral, by calculating an integral. Okay, and so that's part B of definition 7.4. Okay, so as a side note to that, if you want to know the probability that A is less than X less than B, right, that capital X takes a value between A and B, that's equal to the probability that X takes on a value between A and B and that capital Y takes on any value. Right? So we're including this because we're going to calculate this probability using the joint probability density function. And so this is integrating from negative infinity to infinity, then integrating from A to B of little f of x comma y dx dy. We're integrating with respect to x from A to B, and we're integrating from negative infinity to infinity with respect to y. And so we can switch the order of integration. We can integrate first with respect to y, then with respect to x. And so we're just going to switch the order of integration. And so we can do that here. And so now I'm switching here, so now I'm integrating with respect to y, then integrating with respect to, that's an x, sorry. And then integrating with respect to x. And so first, to do that, you calculate the integral inside. Well, what is that? Well, that, by definition, right, remember the definition of marginal probability. By our last definition, I'm going to label this as last definition, there's not a new definition. This is f sub capital X of little x is equal to the integral from negative infinity to infinity of f of x comma y dy. Okay, so this thing in parentheses is this, right? And what is that? That's f sub capital X of little x. And so this is equal to the definition from A to B of little f sub capital X of little x dx. Okay, and so what we just showed, therefore, what we concluded is that the thing that we started with, the probability that A is less than X less than B, is equal to this definite integral. The definite integral from A to B of the marginal probability density function of X evaluated from A to B. Okay, so to find the probability that A is less than X less than B, you just integrate with respect to X from A to B the marginal probability density function of X. Okay, and so this is an important equation to know. This is good to know. How do you find that probability with the marginal probability density function? You integrate it from A to B, like that. Right? And how do you find this probability? You can find it by integrating that. And so together with this definition and that, you can find the probability that X is between A and B. First, you find this by integrating your joint probability density function, and then you plug that in here, and you integrate from A to B to get that probability. Okay, so you combine this definition with that equation, and you can find that probability with the joint probability density function. Okay, so in your notes, make sure you have this definition and that equation. You should have other things too, but that's definitely those two things, right? And very similarly, you can do this for y. So you could show that the probability, similarly, you can show that the probability that a is less than y, less than b. Actually, I'll use c. Probably c is less than y, less than d, is equal to differential from c to d of f sub y of y dy. Okay, so we can justify this in a very similar manner and show that the probability that c is less than y less than d is the integral from c to d of f sub capital Y of y dy. Okay, and that would be from, you use the definition here to justify a capital Y, f sub capital Y of y is equal to integral from negative infinity to infinity of f of x comma y dx. Okay, and so you do a very similar thing here. You would use that definition and you would end up with this conclusion. Okay, so let's go to the next example, example 7.14. So example 7.14. Find the marginal probability density function of random variable x of example 7.5. Find the probability that capital X is greater than 2. Okay, so I'll tell you what you need to know from that example, okay? So solution. Okay, so the problem is find the marginal probability density function of random variable x of example 7.5. Find then the probability that x is greater than 2. So this is what you need to know from that example. The joint probability density function of x and y is f of x comma y is equal to e to the negative x, e to the negative y times e negative y for x positive and y positive. And it's 0 elsewhere. Okay? So that's what you need to know from example 7.5. The joint probability density function of x comma y is that. Okay? That's from example 7.5. And we want to find the marginal probability density function of that random variable x. Okay, well, from the definition we know, so we want to find the marginal, first we're going to find the marginal probability density function. So that's f sub capital X of x, right? The marginal probability density function of random variable x, that is f sub capital X of little x. That's the marginal probability density function of random variable x. And so we're going to find that, and by definition, right? By the definition of it, it's the integral from negative infinity to infinity of little f of x comma y dy. Okay, just we're in the definition, right? That's the name. This is the notation for that, and by definition it's equal to that. And so you calculate that integral, and so we get a piecewise function here. You integrate here. You integrate from negative infinity to infinity of that e negative x e negative y dy. And when you integrate that, you restrict the domain for only y positive. So you get the integral from 0 to y, e negative x, e negative y dy. Because we're integrating with respect to y, it's 0 when y is not positive. So we're integrating from 0 to y of that. And when you calculate that definite integral, you're going to get let me just go right to the chase and put a 0 here because you're not technically integrating negative infinity. So let me just put a 0 there. I guess I could put f of x. No, that's good. Okay, that's good. So when you integrate from negative infinity to infinity of f, it's 0 unless y is positive. And so when you find this whole integral here, you're only integrating from 0 to infinity. And so when you calculate that, you get e to the negative x. And this is for x positive. When x is positive, f sub capital X of x is equal to e to the negative x for x positive. And then when x is not positive, you're integrating over 0. And so then that means that you get 0. And so it's 0 elsewhere. Okay? It might be difficult to write this answer, so I'm showing you how you can just show you work here in an easy to read way. Right? F sub capital, the marginal probability density function of random variable x by definition equal to that, and then it's equal to, well, f is a piecewise function. This little f, the integrand is a piecewise function, and so the 0 elsewhere, right, is equal. Then here, you're integrating from 0 to infinity of this, and you're getting that, but that's only when x, the input of the function, is positive, and when x is less than 0. Okay, and so now we found the marginal probability density function of random variable x. It's that. Okay, the next part is find the probability that x is greater than 2. So the probability that x is greater than 2 is equal to the integral from 2 to infinity of f sub capital X of x dx. Okay, this is the marginal probability density function of random variable x. And so to find the probability x is greater than 2, you integrate from 2 to infinity of that. And so that's the integral from 2 to infinity. Well, this, from 2 to infinity, this x is always positive there. And so we just get e to negative x. So this is e to negative x dx with respect to x. When x ranges from 2 to infinity, x is always positive, which means f sub capital X of x is e to the negative x. You substitute that integrand for e to the negative x, they're the same by substitution. Now now you just calculate that improper integral. And so I'll show you the work for that. So then this is the limit as capital M approaches positive infinity of the integral. I'll write positive infinity here so it's clear. You don't have to write positive. If you just write infinity, it's assumed to be positive infinity. This is the limit as capital M approaches positive infinity of the definite from 2 to capital M of e to negative x dx. I chose capital M because my first name is Michael. It's also used. Capital M is used there also. Okay, so when you calculate this definite integral, is the limit as capital M approaches positive infinity of that definite integral. So you calculate using the fundamental theorem of calculus. You can calculate this definite integral. An antiderivative of e negative x is negative e to negative x. You take the derivative of negative e to negative x, and you're going to get e to negative x, right? So this is an antiderivative of that, and you evaluate from 2 to capital M. And then after you do that, you take the limit as m approaches positive infinity of that. Okay? So I'm going to erase the top part here. I was hoping that I could fit all that in at the bottom there. I'm going to need some more room, so I'm going to finish this calculation up here at the top. Okay, so that's the thing. So now here, I'm going to continue that over here. Okay, so this limit of this is equal to, now so limit as m, I haven't calculated the limit yet, right? So you keep the limit there until you calculated it. And so I'm still working, now I'm working on this. So now I'm going to plug in capital M, so you get negative e to negative capital M, minus, you plug in 2, negative e to negative 2. Okay? So by fundamental theorem of calculus, you get that. Now I'm just going to simplify what's in the brackets. So this is equal to the limit as capital M approaches positive infinity. So I'm just showing you again how to calculate this improper integral. Okay? This is an improper integral of type 1 in calculus 1. Okay? It's an infinite integral. It's integrating over an infinite length interval. Okay. Take the limit of that. Okay, so then this equals to the limit as m approaches positive infinity of this. Well, the minus is a plus. So you get e to negative 2 minus e to negative capital M. And so you're taking the limit as m approaches positive infinity of that. But what is the limit as m approaches positive infinity of e to negative m? Right? The limit as m approaches positive infinity of e to negative m is equal to the limit as m approaches positive infinity of 1 over e to the m. Right? And as m gets larger and larger, the denominator gets larger and larger, so 1 over that gets smaller and smaller, and so this limit is 0. So the limit of that is 0, and the limit of the constant is itself. And so that's equal to, now calculating the limit of that, that's e to the negative 2 minus 0. So you have e to the negative 2. Okay? And so the answer is that the probability that x is greater than 2 is equal to this improper integral, and when you calculate it, you get that's equal to e to the negative 2. Okay, and as a decimal, e to the negative 2, if you put that in your calculator, you'll get 1.353 as the first 4 decimal places rounded to the nearest first 4 decimal places, 0.1353. Okay, and so that is the answer to the exam. Those are the answers to the questions in example 7.14. Okay, so we're done now with that section. Okay, so hopefully it was helpful in this lesson that I calculated these integrals. It can be a little difficult sometimes to calculate a double integral. You know, when you have a region like the triangle problem where you have to, it was dotted, these, right? In between that, it was dotted the outside. But you have to integrate over that, right? And you have to know how to you have to know how to calculate double integrals and difficult ones. And you have to be able to calculate improper integrals like this, right? It's the limit of a definite integral. Right? And if it's from negative infinity to infinity, then you're going to have to take a double limit, as the lower limit goes to infinity and the upper limit goes to infinity, and everyone has the upper limit goes to infinity. Right? So you have to know all that. That's from calculus. Okay. All right. So, but I showed you, I reminded you a little bit of it here in this lesson. Help you. Okay. So that example is done. Okay, so 7.2.5. So 7.2.5 is on conditional distributions. Okay, so conditional distributions. So let x and y be discrete random variables. So x and y are discrete random variables. So the probability that capital X equals x naught, given that capital Y equals y naught, that's equal to the when you have discrete random variables x, y. This is the probability that capital X equals x naught, and y, capital Y equals y naught, divided by the probability that capital Y equals y naught. And this is equal to little f of x naught comma y naught over little f sub capital Y of y naught. And this is provided the probability that capital Y equals little y naught is positive. Basically non-zero, but the probability is already never negative, and so when you have it, it's already never negative as a probability. But if you want it to not be zero, because there's a number here, if it's not negative and not zero, then it's positive, right? So I'm saying it's positive. I've really just restricted it to say that it's not zero, where a probability function is already never negative. So okay. So this is the conditional probability that x equals x naught, and this is the probability x equals x naught given y equals y naught. So that's the probability that x equals x naught and y equals y naught divided by the probability y equals y naught. This probability in the numerator is a little f of x naught comma y naught, right? That's the probability that x equals x naught and y equals y naught. And then the marginal probability density function of capital Y is that. It's the probability capital Y equals little y naught is little f sub capital Y of little y naught. And that's what this is, this probability. Okay, and so this is a conditional probability involving the joint probability density function and the marginal probability density function. Okay, and also okay, so f sub capital X of x given y naught is equal to the probability capital X equals little x given that capital Y equals y naught. That. And that's equal to f of x comma y naught divided by f sub capital Y of y naught. But now here little x is a variable, so you don't have to look at a particular value of x. You can look at any value of x here. Okay, so this is a definition. And so that equaling to that is the conditional probability function of x given y equals that. Okay, so the marginal probability density function of x for the random variable x is probably x given y naught is probably x equals x and y given y equals y naught. That's the conditional probability function of x given y equals y naught. Okay, again, it's the probability that capital X equals little x given that capital Y equals y naught. Y naught is a fixed number, and x is little x is variable, it can change. Okay, and so above that, I'm just going to write one additional thing here. It won't involve two equations. Okay. So let me wrap up this definition. So continuing this definition, f sub capital X of x given y is equal to f of x comma y over f sub capital Y of y if f sub capital Y of y is positive for all x. Also, f sub capital Y of y given x is equal to f of x comma y over f sub capital X of little x if f sub capital X of little x is positive for all y. And this is for both of these are both equations are for discrete and continuous random variables x and y. Okay, so so the conditional probabilities are these for both discrete and continuous random variables x and y. All right, these equations will hold. Of course, when you compute the marginal probability functions for continuous and discrete, you'll be computing these two in two different ways, depending on whether you'll be computing this differently whether it's discrete or continuous, and you compute this differently whether it's discrete or continuous. But this fraction would be the same whether it's discrete or continuous. Okay, so I'll leave this on board for a moment. You should write these equations down. Okay, and this is how you compute conditional probabilities. Okay. Okay, and so in the next video I'll continue and we'll do some examples of this using the definition of conditional probability. Okay, so I'll see you next time.